So in this video we'll do a few exercises on the z transform, and the first thing that we'll do here is solve a difference equation with a shift to the right by 1 and by 2. So the first thing that we have to do is to go to the z domain, of course. So we'll have y of z minus 5 times, then we have to take the z transform of this one, so it will be z minus 1 y of z, and we'll have to add something, because when you shift to the right, what is in minus 1 comes in 0, so you'll have plus y of minus 1 z to the 0, so that's 1. We have done this several times in full detail in the theoretical course and in 2 examples that we've done in the previous video, so be sure that you can do this at the time of the exam. So here we'll have z minus 2 y of z. So we'll have in position 0 what was in position minus 2, so we'll have to add y minus 2, right? And what was in position minus 1 will be in position 1, so y minus 1, and since it's position 1 now, z minus 1. Again, we have done this in full detail, and the z transform of the unit step is the sum that goes from n to equals 0 to infinity of un z minus n, so it's a sum that goes from n to equals 0 to infinity of z minus n. Remember that the sum of the geometrical series, it's 1 over 1 minus q if the modulus of q is smaller than 1, so this is 1 over 1 minus z minus 1, right? And the domain of convergence is larger than 1, so we can write here 1 over 1 minus z minus 1. So this we can erase, and we can group all the terms that are in y of z. There is a 1 here, there is minus 5 z minus 1, and there is plus 6 z minus 2 y of z. All the terms with the initial conditions will take them to the other side, so 5 times y of minus 1. This is why we have to put the parentheses, so that you don't forget to multiply by 5. So, and now this one over here. So this is 15, this is 12, but if you look at it, it's a minus over here. And this one is correct. So this is minus 18. Right, so this one we can factor in 1 minus 2 z minus 1 and 1 minus 3 z minus 1. And then you have to check, of course, and this seems to be okay. Right, so please, whenever you factor, check that everything is correct. So we have a 3 here, minus 18 z minus 1 plus 1 over 1 minus z minus 1. And if you put everything under the same denominator, you'll have 1 minus z minus 1. I'll leave you the calculations, but you'll have 4 minus 21 z minus 1 plus 18 z minus 2. So now you can write y of z as, well, the numerator plus 18z minus 2, and now divided by 1 minus 2 z minus 1, 1 minus 3 z minus 1, and this one over here. Right? And this you can now do a partial fraction expansion. It's a third order polynomial. Remember, here we shift to the right, so it's more natural to work with the variable z minus 1. And indeed, in the denominator we have the third power of z minus 1, so we have a third order. We expect 3 constants. And this is indeed the case. I will not compute them all, and not in full detail, but what you have to do here is hide this one. So write the numerator. If you hide this one, this will be left. And now we have to evaluate at the root of the denominator here. So it's z minus 1 is equal to a half. Right? And if you go through the calculations, you will have 8. You can do something similar for b. You will have minus 9 over 2, and for c you will have 1/2. Okay, so now we are ready to do the inverse z transform. Right, so maybe first write it again. So we have y of z is 8 over 1 minus 2z minus 1 plus minus 9 over 2 over 1 minus 3z minus 1 plus a half over 1 minus z minus 1. So now we can do the inverse z transform. And you remember that the z transform of alpha k uk is 1 over 1 minus alpha z minus 1. So y of k will be 8 to the power n minus 9 over 2 3 to the power n plus a half 1 to the power n, but that's 1, right, times un to make everything Gaussian. We are not finished. What we have to do is, well, check if we meet the initial conditions. From the original equation we can write that, I should write, of course, an n over here. So from the original equation you can write y of n is equal to u of n plus 5yn minus 1 minus 6yn minus 2. This allows you to obtain y0. So y0 is u0 plus 5 times y minus 1 minus 6 times y minus 2. Okay, so that's 1 plus 15 minus 12. Yes, that's correct. And that's a 4. And you can also, we have obtained this by plugging in n is equal to 0, of course. We can also obtain y1. y1 is u1 plus 5 times y0 that we have just computed minus 6 times y minus 1. So this is 1 plus 20 minus 18, so that's a 3. And if you have a look, y0, that is 8 minus 9 half plus a half, that is indeed 4. And y1 is 16 minus 27 over 2 plus a half, and that's indeed 3. So we have checked that we meet the initial conditions, so we're kind of, well, more or less sure that this is indeed the correct response. So here's another exercise. The question is, well, if you know that the response of a system to the input that is shown here on the screen, so it's 0 everywhere except at index k is equal to 0 where the input is 1, and at index k is equal to 1 where the input is minus 2. You know that the response to that system is y of k, that is given over here. And the question is, what is the impulse response of the system? So we will proceed by computing first of all y of z, right? And this is 2 times, well, z over z minus 2 minus z over z minus 1. This is the z transform of 2k uk, right? And this one is the z transform of a unit step. If you go through the calculations and you put everything under the same denominator, you will have at the denominator, of course, the product of the two here, and at the numerator 2z. Well, x of z is very easy to compute if you remember the definition, at least, of the z transform. There are only 2 terms different from 0 in xk, so it will be x0 plus x1 z minus 1, so that will be 1 minus 2 z minus 1. And since we are working with the variable z, you can also write it like this. Okay. Equivalently, here we could have worked with the variable z minus 1, would have worked as well. You remember that h of z, the transfer function, is the z transform of the output divided by the z transform of the input. So we have y of z divided by x of z. So that's 2z over z minus 2, z minus 1 divided by z minus 2 over z. So we obtain 2z squared over z minus 2 squared z minus 1. And we're looking for the impulse response. So the impulse response will be the inverse z transform of the transfer function. So what we'll do is decompose hz over z in partial fraction, so that's 2z over here divided by z minus 2 squared, z minus 1, and we can write it as a z minus 2 plus b over z minus 2 squared, and this is because we have a square over here, plus c z minus 1. We have a third order polynomial, so we need 3 constants. Okay, so b is kind of easy to obtain. We have to hide the z minus 2 squared, so it's 2z divided by z minus 1 evaluated in z is equal to 2, so that's a 4. Okay, the a, we have to take this one and take the derivative, so 2z z minus 1 derivative evaluated at z is equal to 2. The derivative will be z minus 1 squared times z minus 1 times 2 minus 2z times 1. Okay, evaluated at z is equal to 2, so that's minus 2, yes, over z minus 1 squared evaluated at z is equal to 2, so that's a minus 2 over here. And c, it's 2z over z minus 2 squared evaluated at z is equal to 1, so that's a 2, right? So what we can do, of course, we have to multiply by z. We can write h of z as minus 2z over z minus 2. b is 4, but we'll write it as plus 2z z minus 2 squared plus 2z z minus 1, right? And now we can do the inverse z transform. So h of k, we have 2's everywhere, so we can put it in front, so this will be minus 2 to the power k plus 2k 2 to the power k. We don't need the 2 because it's already in front, so it's a plus over here, yes, and the plus is in front already, so just plus 1 times u k, because we have a causal system here, and this is its impulse response. You know that I'm a big fan of testing or checking things. I would like to check if this is here correct. Remember here that the input to the system is shown over here, but you can also write it as x of k. Well, it's a delta, a unit impulse, and a delta of amplitude minus 2 shifted to the right. So this is the response to a delta, and what we have here at the input is a delta minus 2 times a shifted delta, and the response to this signal should be this over here. So let us check if this is indeed the case. So if this is the response to a delta, the response to x of k should be y of k Well, the response of a delta is h of k, and then this is the response of a shifted delta, so it should be minus 2 hk minus 1. Okay, so let's write this down. So this is 2 times minus 2 to the power k plus k plus 1 uk, right? So this is h of k simply, minus 2 times, so minus 4 times minus 2 to the power k minus 1 plus k minus 1, 2 to the power k minus 1 plus 1 u k minus 1. So what the first thing that we'll do is, well, this one is annoying us. Okay, so we'll write it as we had originally. Plus 1 uk, and we'll say minus 4 plus 1, and I'll write now u of k, but then I'll have to subtract something in delta k, right? Because I have added something at the index k, so I have to subtract it, and what I have to subtract is this here evaluated at 0. And if you have a look at it, you will have minus a half plus 1, it will be 0, so minus 0 delta, right? So now I can do something else. What is annoying over here is the k minus 1, k minus 1. I can change the power because I have a 2 over here, so let's make it 2. 2 to the power k plus 1, so this is still h of k, right? And now we'll simply say minus 2, and we'll say minus 2 to the power k plus k minus 1, 2 to the power 2 to the power k, right? This is because we've changed this one in a 2 over here, and it entered the parenthesis, and plus 2 over here uk. Well, this one and this one will cancel out, and here we'll have, well, we can put still the 2 in front. Here we'll have k minus 1, 2 to the power k, and here we'll have 1 minus 2, so minus 1 uk. So this will be 1, so we have 2 to the power k minus 1 uk. So this is our expression of yk, and we see that indeed it corresponds to what we had here above. Okay, so we seen that what we have computed is indeed correct. Well, let's do another difference equation. It involves shifting to the right, so we'll use the variable z minus 1. Notice that the maximum shift to the right is just 1, so we'll have, of course, only one initial condition. Y of minus 1 is equal to 2, and the input is xn, and xn is the sum of a unit impulse and a unit step. So let us go to the z domain. So we'll have yz minus 2 times, well, we give our write our parenthesis, z minus 1 yz. Z minus 1 is the shift operator, and we'll have a plus here because when we shift to the right, what will appear at index 0 is y minus 1. So it will appear at index 0, so it's z to the power 0, so 1. Plus x of z, so it's the transform of a unit impulse, so that's 1, plus the transform of a step, that will be 1 over 1 minus z minus 1, because we like to work with the variable z minus 1. And if we put this under the same denominator, we'll have 1z minus 1, and at the numerator we'll have 2 minus z minus 1. Okay, let us collect all the terms in yz. So we have 1 minus 2z minus 1. The initial condition will go on the other side, so we'll have 2y minus 1 plus, and this will be, well, 4, and then we'll have here 2 minus z minus 1, 1 minus z minus 1, and this we can put under the same denominator, and we'll end up with 4 minus 4z minus 1 plus 2 minus z minus 1, and this will yield 6 minus 5z minus 1 over 1 minus z minus 1. So y of z is 6 minus 5z minus 1, 1 minus 2z minus 1, 1 minus z minus 1. So this we can write as a over 1 plus b over 1 minus 2z minus 1. We can do the partial fraction expansion because we have a strictly proper rational function in z minus 1. So a is 6 minus 5z minus 1, that's the numerator, over 1 minus 2z minus 1 evaluated in z minus 1 is equal to 1, the root of this denominator, and if you compute that, we'll have minus 1, and b will be again the numerator over 1 minus z minus 1 evaluated at z minus 1 is equal to a half, and this is the root of this denominator, so this will be 7. So yz is 7 over 1 minus 2z minus 1 minus 1 minus z minus 1. We take the inverse z transform, and we have y of n is equal to 7 2 to the power n minus 1 u of n. We see from the top equation that y of n is equal to 2yn minus 1 plus delta n plus un. So y0 will be 2 times y minus 1 plus 1 plus 1. If we evaluate both the unit impulse and unit step at 0, we have a 1, so we'll have a 6 over here, and we should check if this is correct, and we see that we have indeed 7 minus 1. So this is indeed correct. So here's another exercise with a difference equation, but this time we're shifting to the left. So the natural variable will this time be z. So let us take the z transform. So we'll have z squared y of z. We're shifting to the left by 2. So y of 0 will disappear, so we'll have a minus y of 0. It will appear at index minus 2, so we'll have z to the power minus minus 2, so z squared. 1 y1 will also disappear from the z transform. It will appear at minus 1, so we'll have z to the power minus minus 1, so z. Minus 4 times z yz, and here now we shift by 1 to the left, so y0 will disappear and it will appear at the index minus 1, so z to the power minus minus 1, so that's a z over here, plus 4 yz is equal to 0. So again, this you should be able to do at the time of the exam. Here we have done it kind of quickly, but previously in this video course we have done it in full detail, right? So we can rewrite this. We'll group the terms in yz. So we'll have z squared minus 4z plus 4, and we'll take all the initial conditions to the other side. We have terms in z here and here, so we can group them. y1 minus 4y0. Okay, this one is 1, this one is 3, and this one is 1. So this is z squared minus z, and this one you can factor quite easily. It's z minus 2 squared. So we have yz is z squared minus z over z minus 2 squared. So we need to go back to the discrete time domain to do the, and so we'll need to do the inverse z transform, and what we'll do is a partial fraction expansion of y of z over z, and let's write it down. This is z minus 1 over z minus 2 squared. We have a second order denominator, so we need two constants, so we'll have a over z minus 2 plus b over z minus 2 squared. B is quite easy to obtain. You multiply by z minus 2 squared here, so we are left with z minus 1, and you evaluate in z is equal to 2, so that's a 1. And a, well, what you can do is take this one here and take the derivative. Okay, so this is one method that has been proposed in the course, but if you feel more comfortable with other methods that you've seen previously, so feel free to use them. It has to be correct, of course. Okay, so this is not a b, but of course it's the a. Okay, so now we have b, we have a, we can multiply by z and write y of z as z over z minus 2 plus, well, it's z at the numerator, but what we can do is write it as a half to z over z minus 2 squared, right? Because we remember that the z transform of k alpha k uk is alpha z over z minus alpha squared. I say you remember, but you should be able to find this using the, well, derivative of the z transform of alpha k uk. This is something we have seen in the, well, the theory, right? So now what we can do is take the inverse z transform, and we obtain y of k. Well, this will be 2 to the power n. We'll have a 2 to the power n also over here, multiplied by half times n. So we'll put the 2 to the power n in front. We have a 1 over here, and we'll have plus n over 2. And of course you have to multiply by the step. And now to, well, obviously here it's not a k, but it's an n. And now we can check if we meet the initial condition. So y0 is equal to 2 to the power 0, that's a 1, and y1 is equal to 2 times 1 plus a half, and that is indeed equal to 3. So now we are ready. Check. We have something that meets the initial conditions. Let us do another difference equation. This time it involves shifting to the right. So we'll go to the z domain. So we'll have 2 times, we'll put the parenthesis, z minus 2 y of z, and then what is in index minus 2 will appear in index 0, so we have to add y of minus 2, z of 0, and what is in index minus 1, so y minus 1, will appear in index 1, so z minus 1. Then we again open the parenthesis, z minus 1 y of z, and what is in minus 1 will appear, so we need to a plus sign, and it will appear at index 0, so z to the power 0 is 1 minus y of z, and then we have the z transform of this one, and this is z over, well, not maybe z, because since we shift to the right, we'd better write everything in terms of z minus 1, so we can write it as 1 over 1 plus z minus 1. So let us collect all the terms in yz. So we have 2z minus 2, we have minus z minus 1, minus 1, and then we'll take all the initial conditions on the other side, so we'll have minus 2 y minus 1 z minus 1 minus 2 times y of minus 2, and we'll have plus y of minus 1 plus 1 over 1 plus z minus 1. This one we have a 2 in front of here, so beware. 2 times z minus 1 plus 1 z minus 1 minus 1, so we can factor it like that. Please check, and here indeed it is correct. So y of minus 1 is 2, so here we have a 1 and here we have a 2, so these two will cancel out, so we have here minus 4 z minus 1 plus 1 over 1 plus z minus 1. So y of z can be written as minus 4z minus 1. Well, we can make it a plus over here. We don't like z minus 1 minus 1. We'll write it as 1 minus z minus 1. So this is why we have the change of sign here. And here we'll write it as 1 plus 2z minus 1. And here we'll put a minus sign for the same reason. So it's 1. And then we'll have 1 plus 2z minus 1, 1 minus z minus 1, and 1 plus z minus 1. Okay, so what we can do is, well, put it under the same denominator. What you could do is take the partial fraction expansion of this one and of this one. This time I chose to put it all under the same denominator, and you'll end up with minus 1 over 1 plus 2z minus 1, 1 minus z minus 1, and 1 plus z minus 1. And this you can write as, well, a over 1 plus 2z minus 1 plus b over 1 minus z minus 1 plus c over 1 plus z minus 1. So it's a third order denominator. Remember that the variable is z minus 1 and the highest order is z minus 3, so the third power of z minus 1. We need 3 constants, and this is indeed what we've got. Remember that a is obtained by multiplying this expression here by 1 plus 2 z minus 1, so the numerator divided by 1 minus z minus 1, 1 plus z minus 1, and you have to evaluate it at the root of the denominator. Z minus 1 is equal to minus a half. I won't go over the details, but you will have minus 8 over 3. You can do the same for b. You'll have 7 over 6, and for c you'll have a half, right? So y of z is equal to minus 8 thirds 1 plus 2 z minus 1 plus 7 over 6 1 minus z minus 1 here, and plus a half over 1 plus z minus 1. We can do the inverse z transform, and you obtain yk is equal to minus 8 thirds minus 2, and again it's an n here, plus 7 6 plus a half minus 1 to the power n un to make everything causal. Here we have 1 to the power n. Okay, so we have to check the initial conditions. You can obtain from this equation here above yn. So yn is equal to 2 yn minus 2 minus yn minus 1 minus 1 to the power n un, and now you can obtain y0. So it's 2 times y minus 2 minus y minus 1, and we have here minus 1 to simply, right? So this is 2 minus 2 minus 1, so it's equal to minus 1. So let's check if this is correct in our solution. So we have minus 8/3 plus 7/6 plus a half. If we put that in at the same denominator, we have 6 over here, minus 16 plus 7 plus 3, so this is indeed equal to minus 1. You can obtain also y1. This is 2 times y minus 1 minus y0, and if you take this one and you take 1 inside, you have plus 1. So you have 4 over here, y0 is minus 1, so plus 1 plus 1, so that's a 6 over here. So is this correct? Well, we have minus, I'd say plus now, 16/3 plus 7/6 minus a half, and if you put that under the same denominator, we have 32 plus 7 minus 3/6. So that's correct as well. Okay, so indeed we have checked, we meet the initial condition, so we can put a big check over here and see that this is indeed correct. Well, let's do another exercise just for the fun of it. And here we have a difference equation, but we shift to the left, so we will work with the variable z. Okay, so if we go to the z domain, we will have, well, z squared, right? And what is in index 0 will end up in index minus 2, so we'll have to subtract it. Okay, y0 will end up in index minus 2, so it will be z to the power minus 2, so z squared. y1 will disappear also, and it will end up at the index minus 1, so it will be z to the power minus 1, so z, right, minus 3/2. Let's put the parenthesis, so we'll have z, of course what is lacking over here is y of z, so z y of z, and y0 will disappear. It will end up at the index minus 1, so z to the power minus 1, so z plus a half yz is equal to, we work with the z variable, so z over z minus a quarter. So let's put everything which has a yz up front. So we have here z square minus 3/2 z plus a half. We put the initial conditions on the other side, so we have z square y0, and we will have z times, well, y1 minus 3/2, and don't forget to multiply y0 plus z over z minus a quarter. So this is well, this will be 15, right? This is 4, so, and this is 10 here, so we have 10 z square minus 11 z plus z over z minus a quarter, right? This one we can factor as z minus a half times z minus 1, and we obtain yz, and let's keep the two terms this time, over z minus a half z minus 1, and here we have z not equal plus z over z minus a quarter, z minus a half, and z minus 1. We'll call this y1z and this y2z. Well, y1z over z, we can decompose it as a over c minus a half plus b over z minus 1, right? So a will be, so y1 over z is 10z minus 11 over z minus a half z minus 1. We multiply by z minus a half, so we have here 10z minus 11 over z minus 1, evaluated that z is equal to a half, and if you compute that you'll end up with 12, right? And b, you'll have 10z minus 11 over z minus a half, and now z evaluated at 1, and this will give you minus 2, right? So y1 of z is equal to 12z minus z minus a half minus 2z z minus 1. So if you do the same for the other one, you'll have terms in z minus a quarter, z minus a half, and z minus 1. I'll leave you the exercise, but you'll have, well, 12z z minus a half minus 2z z minus 1, and then you'll have minus 8 z over a half, 8/3 z minus 1, yeah, and plus 16/3 z over a quarter. Okay, so they have the same denominator, and these have the same denominator, so we can rewrite it as 4z z minus a half. Okay, so this one I'm leaving you as an exercise, right? It's a z here also, and so this is the expansion of y to z, and here we'll have, well, plus 2/3 over z minus 1, and then plus 16/3 over z minus a quarter, right? So now we can do the inverse z transform, and we obtain yn 4 times a half to the power n plus 2/3 1 to the power n, but that's 1, plus 16 16/3 1/4 to the power n, and then times un to make everything coarse. So are we done? No, we're not. So y0 is equal to 4 plus 2/3 plus 16/3. So that's 4 plus 6, right? So that's 10. Y1 is 2 plus 2/3 plus 16/3 divided by 4, so 4/3. So 2, and this is also 2, so this is 4. And indeed, we meet the initial conditions.